Alrighty, howdy folks. Section 5.2 and 5.3, that's the goal today. You will see that 5.2 is actually pretty small, so it shouldn't, in fact, both of them together shouldn't take a whole lot of time. However, don't let the size of these things downplay the importance of these concepts, okay? All right, definite integral. Does that term integral sound familiar to you? Yeah, in what was that, 4.9, I introduced the concept of an indefinite integral, right? What was the idea there? The idea was simply like, hey, what is integral of sine x? You'll say, wait a minute, what's the derivative of what is equal to sine x? And the answer was negative cosine x, right? The derivative of negative cosine x is positive sine x. So we'll say the integral of sine x dx, that means with respect to x, is negative cosine x, and we add a plus c. Now that was an indefinite integral. What's with this definite integral? That's what we're going to explore today. Cool? Let's see. What? This is the stuff we talked about in Riemann sum. You know, showed some interval a, b, and split that interval into n equivalent or subintervals, and then the width of each is blah blah, and then yeah, this is stuff that we saw before in the previous section, right? What's that got to do with the definite integral? That's the idea. So the definite integral of a function f on an interval ab is defined as, and the way you read this is integral a to b of f of x dx. Cool? Integral a to b of f of x dx. And what is that? That's nothing but the limit of the Riemann sum as n approaches infinity. And we said Riemann sum, one way to calculate the Riemann sum is by using the right points, which would give us I used left points here. How do these things escape me, man? I tell you, I thought I took care of it, I went over it and all of that stuff. But somehow mistakes like that keep creeping in. I'm sorry, guys. All right, let's go with this. So I equals 1 to infinity of f of x by delta x. That's when we use right end points. Okay. But the thing is, the limit at infinity of the Riemann sum, we saw that was exactly the same as the area under the curve, right? So what is this definite integral doing? Well, guess what? It also gives you the area under the curve. Okay, area under what curve over what interval? Same as before. If you have a function f and defined on the interval ab, and you want to find the area under that curve on this interval ab, you can actually use this concept of definite integral. Is this definite integral related to the indefinite integral? Yes, it is. And that's exactly what I'm about to show you next. Okay, the definite integral, actually the textbook and all mathematicians don't want to introduce this concept yet. Oh, this chill. Okay, this is nothing but integral a to b of f of x dx is nothing but the antiderivative f evaluated at the upper limit b. Okay, what is the antiderivative? We will say that that's the same thing as that indefinite integral. Okay, the only difference is plus c. So the integral evaluated at b minus the integral evaluated at a. So let me repeat that. The definite integral a to b of f of x dx is the indefinite integral evaluated at b minus indefinite integral evaluated at a. I said uppercase F is the antiderivative, and you know antiderivative and integral are more or less the same. In an antiderivative, you won't have that plus c, whereas in a indefinite integral, you will have a plus c. That's the only difference, right? That's the whole point of this section, folks. Okay, I'm going to give you a few examples and go through with it. So one of the things, of course, we definitely need to talk about is what kind of properties do these definite integrals have. For one thing, whatever were the properties of indefinite integral that we looked at, they all apply here. Like what? What was the integral of a sum? Was that equal to sum of the integrals? Yep. Oh, okay. So in indefinite integral, if that is true, they are true even in definite integrals. The integral of a sum or difference is equal to difference or sum of the integrals. What does that mean in turn? In the sense, if you are expected to take the integral of a sum of two quantities, let us say two functions, you can take the integral of each of them separately and then add them up. That was the idea, right? Okay, what else did we learn? If you have a constant multiple, you can pull that constant multiple outside of the integral. Does that work for definite integrals? You bet. Right? It works even for definite integrals. Integral of a product, was that equal to product of the integrals? Nope. Definitely not. Right? Just as derivative of a product is not equal to product of the derivatives, integral of a product is certainly not equal to the integral of a product is not equal to product of integrals. Similarly, quotient. Okay? However, there are a few extra properties for definite integrals. Suppose you want to integrate from a to b, then you can actually integrate from a to c and add to it integral c to b. Sometimes this is very, very useful. Okay, so you can add the integral from a to c and integral from c to b in order to get integral from a to b. It kind of makes sense, right? If you're looking at area under a curve, could you not just break it into chunks and add them up? Hey, what's the area from A to B? Well, let me figure out what's the area under A to C, and then from C to B, and add them up. Yeah, it's the same idea here. Okay, cool. Next, what's the other property? It turns out integral of a to b of f of x dx is the same as negative of the integral from b to a of f of x dx. In fact, that should not surprise you. I'll tell you why. Okay, first, take a good look at this result. Integral a to b of f of x dx is negative of integral b to a of f of x dx. That's because, let me go back and show you. Let's go to this guy. If I have f of b minus f of a, that's what integral a to b is, can I think of this as negative of f of a minus f of b? Can I factor out a negative sign out of this? Yeah, I can write this as negative of f of a minus f of b. Okay, f of a minus f of b, isn't that integral b to a of f of x dx? So we just have a negative of that thing. That's where this came from. Okay, if you understood it, that's fine. If you didn't, don't worry too much about it. Okay, so we have this additional property for definite integrals. And one more thing. One of the things that we kind of assumed was when we said area under the curve, we assumed that f was positive. And that interval a to b, f was positive. But what happens if f were to be negative on that interval ab? then the area under the curve is taken to be negative. In fact, it won't be area under the curve. It would actually be area above the curve up to the x-axis. Okay, so here is a picture of it. Suppose our A is 0 and B is some value here, and if you're looking at area under this straight line, you shouldn't look area below this one. You should actually look area above this one up to this horizontal axis, the x-axis. And that area would be treated as being negative. So back in all through our life, nobody could ever tell us that area could be negative, right? What's the area of this square? Oh, it's -4 square inches, man. If somebody said that to us, we would have probably beat them up, right? But a negative area in this context actually makes perfect sense. It just happens to be the area above the curve, and the function happens to be below the x-axis. Okay, all right. Then let's do one thing. In 5.1, boy, we had a big time. We had a hard time figuring out the area under the curve using the Riemann sum, right? It was a pretty long process. The same thing, check this out. If we were to use this definite integral, that whole problem is going to be a piece of cake. So, find the area under the curve, x squared plus x minus 1 over the interval 1 to 3 using the definite integral. So based on our definition, all we need to do is to find the area, do this definite integral from 1 to 3 of f of x dx, which is integral 1 to 3 of whatever f of x is, x squared plus x minus 1. Okay. Could we just evaluate the derivative, the integral here? Do we know the integral of x squared? Yeah, we can apply the power rule. Can you recall what the power rule was? Integral of x to the n dx is x to the n plus 1 over n plus 1. Right? So this should be x to the 2 plus 1 over 2 plus 1. That means x cubed over 3. Integral of x similarly is x squared over 2. Integral of 1 is just x. So we'll say x cubed over 3 plus x squared over 2 minus x. Hey, what about that constant, man? The thing is, you can ignore the constant when you're doing the definite integral. Maybe at a later point, I'll actually show you why it is that you can ignore the constant. The simple answer is that actually cancels out. You'll have a plus c and a minus c. And so that just adds up to 0. Plus c minus c, they add up to 0. Okay, so that's why you don't have to put that integration constant when you're doing a definite integral. Cool. Okay, but what do you mean by these limits now? Oh, we got the antiderivative. All we need to do now is to evaluate this antiderivative at the upper limit, which is 3, minus the same antiderivative evaluated at the lower limit, 1. Okay, so what I'm simply saying is plug 3 for x, figure out what's inside. From that, subtract, plug 1 in for x. That's it. So 3 cubed over 3 plus 3 squared over 2 minus 3. That's what you get when you plug in the upper limit 3. And 1 cubed over 3 plus 1 squared over 2 minus 1. And sure enough, we are subtracting, right? That's it. Whatever this turns out to be. I think I may have gone ahead and said, okay, 3 cubed over 3 is 3 square, which is 9. And 9 over 2 minus 3, blah, blah. So it turns out to be 32 over 3. Look at how, because I explained in between, it took at least this much time. But if I didn't, this would have been done within a few seconds. Whereas with the Riemann sum, boy, it took a long time to work that problem out. That's the beauty of definite integrals. Okay, cool. Let's pick another problem that we had done. We had x cubed minus x squared plus 3. So we do integral 0 to 2 of f of x dx. X cube integral is, tell me, x cube integral, power rule, x to the 4 over 4 minus x cube over 3 plus 3x. Evaluated from 0 to 2. That means plug the upper limit 2 for x minus plug the lower limit 0 for x. Ta-da! 0 to the 4 over 4, that's 0. 0 cube over 3, 0. 3 times 0, 0. This whole thing is just 0. So, this just becomes 22 over 3. Cool? Can you do this? I'm sure you can, right? Guess what? That section is done. Okay? So with that, let's move on to 5.3, which is the fundamental theorem of calculus. Okay? And in this one, the first part would be not familiar to you, but the second part of this fundamental theorem of calculus is exactly what we did in 5.2. That means that definite integral, that's what this whole thing is about in the second part. The first part, there are two parts to this fundamental theorem of calculus. The first one looks like this. Does that look scary? When I first looked at it, I must admit, I was like, what the hell is this, man? The derivative, integral, blah, blah. Well, here is the idea. I'll go over this one. All this is trying to say is something like this. The derivative of integral of a function is the function itself. The derivative of the integral of a function is the function itself. Really? Yeah. Let's say the derivative of integral of cosine x, if I were to say. Right? Are you with me? Derivative of integral of cosine x dx. Let's go through the process. Okay, derivative of, let's evaluate the inside stuff. Integral of cosine x dx. We know integral of cosine x is sine x. Right? Integral of cosine x. Why is that? Because the derivative of sine x is cosine x. So the integral of cosine x is sine x. Okay, what's the derivative of sine x? Oh, that's cosine x. Isn't that the function? Derivative of the integral of the function is just the function itself. That's all there is to it. This is saying the same thing but in a slightly more general situation. Okay? Alright. So here is the idea. If you need to take the derivative of a certain definite integral, which from g of x to h of x of f of t dt, okay, I'll give you quite a few examples, is nothing but the composite function f of h of x, you know f of t, use that to find f of h of x. You will also know h of x. So when you know f of t and you know h of x, you just have to do this, the f circle h or f of h of x, the composite function, right? That's it. That's what the first thing is saying. F of h of x times the derivative of h itself, okay, minus f of g of x times g prime of x. The same thing with the lower limit. F of g of x, g prime of x. I didn't do this here. But let's say, yeah, maybe I'll come to it later. And the second part of the fundamental theorem of calculus is precisely what we said previously. Integral a to b of f of x dx is nothing but f of b minus f of a, where f is the antiderivative. Cool? So those are two things. So let me solve a few problems like this one. What is d dx of integral 0 to x of square root of t plus t square dt? Does this look exactly like d dx of integral g of x to h of x of f of t dt? Integral g of x to h of x f of t dt? Does it look like that? Yep, it does. So we can apply the first fundamental theorem of calculus for this. What is f of t? Is that a fair question to ask? I'm asking you to compare what you see here with what you see there. Okay, with that, f of t is nothing but the integrand. That means what you are integrating. So would you agree f of t must be square root of t plus t square? Yep. Cool. Next, what is g of x? What is g of x? G of x is the lower limit of the integral. What is the lower limit of the integral here? 0. Simple. Cool. What is h of x? The upper limit of the integral. Okay, what's the upper limit here? X. Simple. Are you good so far? Okay, so we have f of t, g of x, h of x. According to this, we need to find some f of h of x and h prime of x. Okay, we need a few derivatives. So let's go ahead and figure them out. If g of x is 0, what is g prime of x? Oh, derivative of 0 is 0. Okay, if h of x equals x, what is h prime of x? Oh, that's d dx of x is just 1. Right? Okay, good. Now, let's see. If we need to evaluate f of h of x, right? But h of x is x. So f of h of x is f of x itself, because h of x is x. Cool. If we know f of t to be square root of t plus t square, can we figure out what f of x ought to be? Hey, just simply replace the t with an x, man. Yep, x plus x square. Square root of x plus x square. Simple, right? For instance, when we have f of t equals square root of t plus t square, if I asked you, hey, what is f of 3? You will say plug 3 for t, and you get square root of 3 plus 3 square, whatever that turns out to be. So if I said what is f of x, you just plug x for t, and you get square root of x plus x square. Right? Okay. What is f of g of x? F of g of x is f of 0, because g of x happens to be 0. So plug 0 for t, and you get 0 plus z square, 0 square, square root of that, and that's just 0. So we have everything that we need on the right hand side to evaluate this derivative. So let's go ahead and figure that out. d dx of this is f of h of x, simple plug and chug, is square root of x plus x square, that's what I wrote, times h prime of x. H prime of x is 1, so I plug that in, minus f of g of x happens to be 0, times g prime of x is also 0, so 0 times 0. So that just simply became square root of x plus x square. Isn't that simple? That's the idea. Okay. Cool. Now, in this case, it turns out we do see something of that kind. What kind? The derivative of the integral of f function turned out to be the function itself. Okay, this is of course a definite integral and specifically from 0 to x. So the thing is, we can replace this integral 0 to x with this whole integral, we can replace it with an indefinite integral square root of x plus x square dx. Okay, so anyways, so this is how you solve this problem. Let's pick another one. Once again, does this look like integral ddx of integral g of x to h of x of f of t dt? Yep. So let's identify each one of these things. What is f of t? T square over t to the 4 plus 1. What is g of x? The bottom one, 1. H of x, the top, square root of x. G prime of x, 0. What is h prime of x? 1 over 2 square root of x. Right? Cool. F of h of x is f of square root of x. And wherever we see x, wherever we see t in f of t, let's plug in a square root of x. And so we get this. Just simplify it a little. Square root of x, the quantity square is x. Square root of x, the quantity to the 4 is x square. So that's what I wrote. And f of g of x happens to be wherever you see t, plug a 1. So 1 square over 1 square plus 1, which is 1 over 2. We are ready to figure out the derivative. And that is f of h of x, x over x square plus 1, times h prime of x, 1 over 2 square root of x, minus f of g of x is 1/2 times g prime of x is 0. Just a matter of plug and chug once we get all these quantities. And so the second term just went to 0 because of multiplication by 0. And so we are done. Cool. What simplification I did? Oh, okay. I said x over square root of x is just square root of x. Okay, that's the simplification I did. Okay, with that, I'm done with the FTC1. FTC is the Fundamental Theorem of Calculus, Part 1. Now, let's look at the FTC2. These are all simple problems. Suppose we need to evaluate integral 1 to 2 of x squared dx. We are not being asked to take the derivative anymore. You see that? Earlier, in the first 1 and 2 problems, we were asked to find the derivative of some integral. But here, we are just asked to find the integral itself, the definite integral. So, integral 1 to 2 of x squared dx, just what's the antiderivative of x squared? Power rule, x cube over 3. Yeah, here recall that power rule. So, x cube over 3. On purpose, I'm adding a plus c. I told you that I will show you what happens if you were to put a plus c. You don't need to. Suppose you were to, what would happen? I told you that I would show you. Here it is. Cool. Apparently, what is it that we need to do? Oh, now plug the upper limit 2 for x minus plug the lower limit 1 for x, right? So 2 cube over 3 plus c minus 1 cube over 3 plus c. Now, would you agree we have a plus c here and a minus when you distribute the negative? Minus c, plus c, minus c. That adds up to 0. Does that happen every time? You bet. Okay, so that is why when we are doing a definite integral, we do the indefinite integral, but the only thing is we will not put that constant c. That's the same thing as saying find the antiderivative, or we can say find the indefinite integral, but just don't put the constant c. Cool? Alright, so the next part is simple. 2 cube is 8, 8 over 3 minus 1 over 3, that's 7 over 3. Done. Is that it? Yep, that's it. Note that the integration constant c cancelled itself out. This happens in every definite integral. We will thus ignore the integration constant whenever we have a definite integral. Okay, that's what I said. Okay, again, would you agree? Power rule. This is in the form of integral x to the n dx, which is x to the n plus 1, x to the negative 2/3 plus 1 over negative 2/3 plus 1. Simplify, simplify. Cool. Oh, 1 over 1/3. Is that 3? 1 over 1/3? So 3 times, isn't x to the 1/3 the same as cube root of x? So that constant multiple 3, I can actually yank it outside of this square brackets now. Okay, and so we have now all we need to do is plug the upper limit 8, cube root of 8, 3 times cube root of 8 minus 3 times cube root of 1. Or I may have said 3 times cube root of 8 minus cube root of 1, right? We can factor out a 3. Cube root of 8 is 2, cube root of 1 is 1. So that's it. By the way, if you were to draw the graph of x to the negative 2/3 and on the interval 1 to 8, if you were to evaluate the area under the curve, it would turn out to be 3. Cool? All right. Problem 5. Okay. Simple, man. You find the integral of 4 minus x and multiply that with the integral of square root of x. Can we do that? No. Big time no. Just stop yourself from being tempted to do anything like that, because the integral of a product is not equal to, big time not equal to, the product of integrals. Okay, so what we need to do is just distribute first, and then we would have a difference, and we will use the integral of a difference equals difference of the integrals concept. So first distribute. Yep, see, that's what I'm saying. Note that integral of f of x times g of x, big time not equal to. I should have had a bigger not equal to sign. Okay, so distribute, and I wrote the square root of x as x to the 1/2, and x times square root of x is x to the 1 plus 1/2, which is x to the 3/2. This form makes our life easy so far as finding the integral is concerned. Would you agree? Because it's clearly in the form of x to the n. Okay, 4 times x to the 1/2 plus 1 is 1/2 plus 1 is 2/3, or 1. Sammy, come on, wake up. 1/2 plus 1 is 3/2. So we have x to the 3/2 over 3/2. But instead of saying over 3/2, I'm saying times 2/3, the reciprocal of it. Okay. Similarly, x to the 3/2 plus 1, 3/2 plus 1 is 5/2. So x to the 5/2, instead of over 5/2, let's say times 2/5, which is the reciprocal of 5/2. So that's what I did. And we need to evaluate this from 0 to 4. So just a matter of plugging in 4 for x in both the terms, minus plugging in 0, but we recognize that when you plug 0 for x, this goes to, first term goes to 0, the second term goes to 0. So I just said minus 0. What is 4 to the 3/2? 2 ways you can do it. You can say square root of 4, which is 2, cube, which is 8. Or 4 cube is 64, square root of 64 is 8. Okay, Similarly, 4 to the 5, oh, that's a pain, right? You don't want to do 4 to the 5. Instead, we can say 4 square root of 4 is 2. 2 to the 5 is 32. So if we did that, we end up getting something like this. Cool? All right. Problem 6. Ooh. We don't have to have just polynomials. Okay? So here, integral of pi fourths to pi thirds of cosecant square x dx. So question time. What in the world is integral of cosecant square x? How should you think about this? The derivative of what is cosecant square x? Wait a minute. Derivative of tangent x is secant square x. Derivative of cotangent x is negative cosecant square x. Wait. This is just negative cotangent x then. Yep. So, the integral of cosecant square x is negative cotangent x, and we integrate from pi fourth to pi thirds. And we evaluate it from pi fourths to pi thirds. So, which means we just plug pi thirds for x and pi fourths for x. Subtract from it where we plug pi fourths for x. Okay, cotangent of pi thirds. That means cotangent of 60 degrees. Cotangent is cosine over sine. So, cosine of 60 degrees over sine of 60 degrees. Cosine 60 is 1/2. Sine 60 is square root of 3 over 2. So, that's going to be 1/2 over square root of 3 over 2 is 1 over square root of 3. What? Yep, I like to figure things out that way. If you're asking me for cotangent of some angle, I figure out what is cosine of that angle over sine of that angle. So cosine of 60 degrees is 1/2 over sine of 60 degrees square root of 3 over 2. When you simplify it, you just get 1 over square root of 3. Similarly, if we need cotangent of pi fourths, which is cotangent of 45 degrees, cosine of 45 over sine of 45. Cosine of 45 degrees is square root of 2 over 2. Sine of 45 degrees is also square root of 2 over 2. So square root of 2 over 2 over square root of 2 over 2 is just 1. So we end up getting this. Right? If you subtract and distribute the negative sign, we can write like this. Simple? Cool. Let's look at this one. Again, remember, the integral of a quotient is not equal to the quotient of integrals. Okay, do not tell me that I'm going to just take the integral of the top and divide that by the integral of the bottom, man. No, man, don't do that. Right? So, what's the way to do this? Well, just split this. Is it okay to write this as x cube over x square minus 2x square over x square minus x over x square? Yep. And that simplifies to x minus 2 minus 1 over x. The integral of x is x square over 2. Integral of 2 is 2x. Integral of 1 over x. Integral of 1 over x. Natural log of absolute value of x. So be sure to say natural log of absolute value of x. What's the next step? Plug 3 for x minus plug 1 for x. Right? That's what we'll do. 3 square over 2 minus 2 times 3 minus natural log of absolute value 3. Natural log of absolute value of 3. Oh, 3 is positive. So absolute value of 3 is just 3. So natural log of 3. Absolute value of 1 is just 1. So natural log of 1. What's natural log of 1? That's 0. Right? So we end up getting this, and when you simplify this, it turns out 9/2 minus 1/2 is 8/2, which is 4. 4 minus 6 is -2, but we would have a +2. So all that just goes away, and we end up with a simple negative natural log of 3. Cool? What? The integral turned out to be negative? The area under a curve is actually negative. Yeah, that's okay. We already talked about this. In fact, I tried to graph this one, and turns out on the interval 1 to 3, the graph of this looks like this. So when it comes to area under the curve, you notice that this portion, the area is below the x-axis, and whereas that area is above the x-axis. So the total area is as such this whole area, negative, minus the positive area. So it looks like the negative area is larger than the positive area, and that's why the whole thing turned out to be a negative area. There is a greater amount of area below the x-axis than there is above the x-axis. Cool? That's the idea behind this. Okay, one more problem. I think this is the last one. Can you bear with me on this one, folks? Okay. Now check this out. Integral of -2 to 2 of f of x dx, where f of x is 2 if -2 is less than or equal to x less than or equal to 0, whereas equal to 4 minus x squared if 0 less than x less than 2. Aha! Whoa. I think I did pick up that problem from the book. I'm hesitating and all this because there's something that I did mention, and this one is kind of forcing me to mention that. Is this piecewise function continuous at x equal to 0? Oh no, what are you talking about, man? Is this continuous? The thing is, if you evaluate this function at x equal to 0, according to what has been said, we must use the top at x equal to 0 because x less than or equal to 0 it says. So when we say tell me what the value of this function is at x equal to 0, we need to use the top and say 2. But slightly to the right of 0, you need to use the bottom one. So if we use the concept of slightly to the right, even though we are not supposed to plug here 0 less than or equal to x, it doesn't say. So, but just for the heck of it, let's try to plug 0 in the bottom one. That turns out to be 4. So there is actually a discontinuity. Okay, there's a jump discontinuity at x equal to 0. But the thing is, even if there is a jump discontinuity, finite number of discontinuities, it's okay. Okay, I should have mentioned that, but let's go with it. All right, so if we need to evaluate the integral from -2 to 2, how do we do that? Oh, you remember that thing? Integral a to b can be split as a to c plus c to b. That's what we're going to do. Since the function is defined differently in different intervals, we must make sure to split the integral into suitable intervals. That is, we need to split this into -2 to 0 plus 0 to 2. And in the interval negative 2 to 0, we have this function to be defined by 2, or defined as 2, and in 0 to 2 as 4 minus x square. Excuse me. And so now we'll just plug, we'll evaluate this integral. Integral of 2 is 2x, go from negative 2 to 0, 4x minus x cube over 3, and just a matter of plug and chug, and simplifies to 28 over 3. That's it. Cool. So you are ready to do some problems on this one, I take it. All right. And let me give you a heads up. The next section we are going to do is 5.5. Now, that one is very, 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 very important. It's a bit challenging, but I really want you to be ready for it. It's called the substitution method. Okay, so do they do, maybe 5. Sorry, maybe we will actually do 5.4, which is just integrals, indefinite integrals that are more complicated, slightly, I mean. I don't know. Anyway, just want to let you know, 5.5 is quite important. In this whole calculus one, if you can do chain rule and logarithmic differentiation and 5.5 substitution rule, you have learned everything just about. If you can score perfect 100 in those areas, you can pat yourself on the back and say, I have learned calculus 1. Okay? It is that important. All right, that's it.